All right, let's get started. Sweet. So we're going to do this last bit really quick. I hope to be just a little bit further ahead. So we'll cruise through this one. If we don't completely follow, that's okay. We're going to be throwing this away and starting on something new right away. So don't worry if you don't completely get this one. We're going to look at a new sort of query. This one, again, gets initialized with an integer. Perfect. And we can go from a stream of A's down to a list of A's. So sure, this is a contextualized value still, but we can actually just unify this with B, say that our value happens to be a list of A's, and it all kind of works out. So we're querying a stream of A's to get a list of A's, and we're going to take the first 3 elements of the stream, or the first 5 elements of the stream, something like that. So this is one of those relative queries I was kind of talking about, which takes the next n slots from the current view. So what it gets is going to depend on where in the stream it is, and of course we're going to get the next 3 elements from the root or something like that. So here's a really simple implementation in terms of foldable. So streams are foldable; they'll just fold forever. But that's okay because Haskell's lazy, so we turn it into a list and we say, oh, I'm going to take the first 3 from that list, and it all works out. So this is one possible implementation of that. This is just a query. Doesn't really have anything special to do with Comonads. But what we can do is we can use extend, right, to extend this contextual query across the entire stream and turn this query into a mutation. So basically what we're doing is we have our stream of numbers that we love so much. We're going to say, oh, well, if we take the first 3 elements of the original stream, we get 0, 1, and 2. But if we extend this query along the entire stream, which remember, this is fmap of this function over the duplication of the stream, then we get this, where we've run take 3 on every possible root of the stream. Does that make sense? So what we've done is we've captured a contextual window of our stream inside each single slot. This is something that is pretty tough to do regularly, right? So you could write this function recursively. As long as it was lazy enough, it would still work. But just like folds and monads and other things like that, it's really nice when we can find the abstraction that matches this, so we don't have to manually write recursive functions and possibly screw them up, right? So we were able to write a very simple take function, which operates over the structure and does the thing once. And by calling extend on it, we do it everywhere, just like magic. Very cool.
What if we take only 0 elements?
Okay, what do you mean?
If we take s from 0, then we...
So the types of that won't really work out. You can't really take multiple things from an integer.
Okay.
So it just won't compile. Yeah. Okay, so let's say we want to do something useful. We want to get the rolling average of a stream. So at each spot, we want to know what the average of the nearest 3 elements are, right? So we say, okay, what window size do we want? Okay, rolling average of window size 3, maybe 5. Here's our input stream of integers, and once we've averaged them, we'll output doubles. It's fine. Cool. So here's an example of what rolling average will look like if we have a stream of those numbers, 0, 2, 4, 6, 8, 10. Once we run the rolling average, we can see, okay, we're doing rolling average of a window size of 2, so we sum the 2 elements that are accessible. So we take 2, so 0 and 2, sum them, divide by the number of elements in the window, and then we do the same on the next set. We do the same on the next set. We do the same on the next set. Then we get this averaged stream. Okay, I'm moving pretty quick here. I hope that's okay. We have stuff to get to. So the type tells us that this is a mutation, right? It says we go from a stream of one thing to a stream of another thing. So that implies to us that mutations are hard, right? Like we have to do this everywhere. I can't even think about doing something everywhere in an infinite structure. But we can do it in one spot using a query, and we can just lift that up, right? So if we can calculate this average on a single stream, we can multiply it out using extend and calculate it on all possible streams. This is what a single instance of this function looks like. Implementation's not important. We're just averaging the window There's nothing comonadic about this. And now that we have a single implementation of this, we want to get from the windowed average to the rolling average, and it's just a windowed average over every possible view, right? So nothing too special. So we'll just lift it up with extend, and away we go. Okay, any really quick questions about that? Cool, okay, awesome. So we can kind of use this to do statistical operations that depend on the context of a single value. You can look at your neighbors and you can decide what to do, and then you can crunch that down. So if you guys want a challenge later, you can implement Comonad for stream. We don't really have time to do that right now. It's relatively simple. I'll let you take a look at that, and you can do it later. There's an implementation available on the repo. Awesome, next up. So we're gonna look at some abstract Comonads now, because Comonads aren't already an abstract enough concept. Let's go deeper. We don't need review, we just did this. Okay. Let's do the review. So we have these methods on our Comonad class. We can extract a value, we can duplicate up, and extend just runs a query in every spot. Okay, I'm going to talk about a special type of query. Again, I'm just kind of coining this, so don't Google it, you're not going to find anything. But I'm going to call them selection queries, and these are unique type of queries. If you haven't seen the forall syntax, don't let it scare you. It just says, given a container full of elements, I'm just going to return one of those elements. I'm not going to mutate it. I'm not going to change it. I'm not allowed to change it because this has to work over any possible insides, right? So one question, have we seen something that matches this yet? Yeah, I see some select, huh? Extract, yes, extract is one. Index is another. There's a few of these. So selection queries select a slot no matter what's inside. So we can have a stream of anything and we can get the fifth element. That's fine. So these are kind of, they have some sort of intuition that these are just selecting slots in the structure if they match this type signature. And that comes in really handy, it turns out. So it just gets the value from whichever slot this query selects. But when you extend over something that selects a slot, you actually rearrange all of the slot positions. So the way that we thought about kind of getting the third element from a stream, well, if we get the third element from the duplicated stream in every position, each position is grabbing the 1, 3 to the right. Each position is grabbing 1, 3 to the right all the way along. It appears as though we've shifted the entire stream, even though we've actually shifted every element in the stream. It's a kind of weird distinction, but basically shifting each slot is equivalent to shifting the entire stream. It just seems like one of them is a little bit less efficient, but they should all work out. So that's not important. Let's keep moving. Yeah. All right. Okay. So if we're going to be doing this a lot, it's really annoying to type extend every time. We have do notation and cool arrows and funky stuff for monads. I want the same. I want the same thing. So we have this, which is, of course, the monad thingy just flipped around. Commits are very clever like that. So we have this this thing, which it does make good sense. We're constructing and running a chain of queries using this. So when we see it in line here, here's the actual type signature. It says, well, okay, so I have some structure on the left, and I have some query, which I want to run on the structure on the right. I will run that query and end up with, oh, that's cut off. There should be a W of B here. And it does the extend for you over the query. So we can see we keep the structure and we move along. So here's what this looks like. We can manually call extend and then pass it the structure, but it's nicer if we can have the structure say I want to run it through this query and end up with another structure. So it's infix extend, just like the arrow equals is infix bind for monad. Okay, here's another example. It shows that it's left associative, meaning we can chain multiple of these and the types work out, which is just peachy. So we can move it 2 to the right, and then we can move it 2 to the right again, and that's the same as doing it in this order. This happens to be a commutative operation, but here we can see the output is that we've moved 4 to the right because we, did it twice. Now remember, this index, right, it's pulling a value out, but because we're extending it, it's as though we're shifting the entire structure. Does that make sense? It's a little bit weird. So because this is extending our index, it's like we're calling drop. Okay. And we can do, of course, the same thing here, where we move 2 to the right, and then we take 3 from every position. Or we can, if we want to then finish the chain by actually getting our focused element, we can throw an AND extract at the end. This ampersand operator is just from data.function, and it's reverse function application. So it says, given a function on the right and a value on the left, flip them and apply. So it's flip dollar. But it's quite common in the Lens library, and it's starting to gain some popularity. Okay, but there's also this one. So you've seen the Kleisli arrow for monad, or maybe you haven't, that's fine. This is the equivalent for Comonads, where we can kind of see a difference here. So this one takes an actual value and runs it through this co-effect and ends up there. This one just takes a query and another query, puts the extend in the right spot, so we get a new query from the input of this one to the output of this one. Questions on these two kind of infixy notation things? Yeah.
Is cofish the official terminology?
It is now. All right. Yeah. That's great. All right. Let's move on. Okay. So we're introducing a new comonad now. This is an abstract sort of comonad. We're not really, we're not in Kansas anymore. We're not talking about actual data structures. So do whatever you need to do to lift your mind to the appropriate level of transcendence, and we'll move on. So what's a store? Well, one intuition that's a little bit common in kind of some of the things in the combinators in the library line up with this is that a store is a warehouse where we have shelves in the warehouse. We're going to try and keep this like kind of spatial thing, even though it's dealing with functions, it's a little bit tricky. And on those shelves we have items, right? We're storing stuff in our warehouse. Great. It's well stocked. Every single shelf has whatever is supposed to be on that shelf. And we have a forklift in our warehouse. We only have one, but it's a quick forklift. And it's always sitting in front of a shelf, okay? So let's test my MS Paint skills here. So here's our warehouse. And inside it, we have this beautiful, beautiful forklift. And it's sitting at the shelf that has books. And that shelf is label number 1. So we have 0, 1, 2, 3. And it's good to go. Okay, so what sort of things can we do with this warehouse idea? What sort of queries can we run? Well, we have this pose, stands for position. This is a function in the Comonad library. And it asks which shelf the forklift is at, okay? So the position of, I'm going to use W to represent the warehouse. So the position of our current warehouse, it's at shelf number 1. We don't know that the shelf contains books. We are talking about what they're labeled, and so the kind of indexes of the shelves are different from the values stored inside them. Okay, we have this extract idea. We want to get something out of this warehouse. Well, we're going to get the thing that the forklift is in front of, okay? So whatever's at the current shelf is what we can get. So extracting from our warehouse gets us books. And we can peek, which gets the item at some other specific shelf. So given that we're positioned at 1, we can say, oh, well, I want you to drive over to 3 and get whatever's there. So it's going to drive down here, it's going to hit 3, it's going to get the laptops out. Okay? It's going to peek at what's at a different position. Okay. And we also have this version, which is peeks. Which gets an item from a shelf that's nearby. So this is one of those things where peek is an absolute query. It says, get me one at 3, no matter where you are, I want you to go to 3 and get this. This one says, well, go to the next shelf and get whatever's there. So implicitly, it depends on the current position of the forklift. So if we peaks 1 from here, we will add 1 to the current shelf number. We end up at 2, we get guitars. Okay, questions about these sorts of things? We'll see some actual type signatures soon, which will probably help with this.
What happens if you peaks +3?
So implicitly, I think I actually have it somewhere in here, this warehouse is infinite. It's a very large warehouse. Or the other option is if we did only have a finite number of values, we would just wrap everything in a maybe, so that we could say, oh, if we go outside of the warehouse, you get nothing. Good question. All right, so here's the actual signature of the store Comonad, where S is the shelf name, and the A is whatever's stored in the warehouse. So we actually define this not as data, but as a function. So we say, for any shelf number, I can get you something, right? So this is a very vast warehouse that has all sorts of things, or maybe we wrap the output with a maybe, just so that we can provide some output for every possible input. So here's an example of what our warehouse looks like. We're just going to make a map using containers. So it's a map from some shelf number, which is an integer, to some value, which is a string, and it just represents what's stored at each of those shelves. Okay, so using just the normal map functions, we can look up at what's at 0. We can look up at what's at 42. Of course, there's nothing there. But this lookup function, it's not partial. It's defined on all possible inputs. Just might return a maybe. So this is what I was talking about is, you can kind of extend in all directions. Maybe should have put that first. Great. So let's build a warehouse out of this lookup function. So we're actually going to bake our inventory into the store Comonad implicitly by partially applying this lookup function with the inventory, and we're going to accept the shelf number that we want to look up. So this is a function from the S, the index, the shelf number, that will eventually result in some value by looking it up in the inventory. So you can see this is a warehouse, shelf numbers that are integers, and things on the shelf are maybe strings. All right, so here are some operations we can do. We can check where the warehouse is. It's at number 1. We can take a look at whatever's in 0, which is just some fidget spinners. And if we look at the next shelf, by adding 1 to the shelf number, we get guitars, just like before. Great. Okay. Questions? Great. Okay. Or maybe not so great if I've lost everyone. Cool. So seek is the absolute version of some of these where it actually mutates our warehouse. So rather than just getting something out of the warehouse, we're actually going to change the state of the warehouse itself. So seek moves the forklift to a different shelf. So given before we were at shelf 1, if we seek 3 on it, we say, oh, forklift go to position 3. And it just does. It doesn't get anything. It's just going to hang out there for now. Okay? Seeks moves the forklift relative to the current position. So you can start to see the relationship between seek and peak, and seeks and peaks. It's a little bit confusing. Seek and seeks work over the position of the forklift. Peak and peaks actually get things out at those positions. So this one, again, assuming we started at 1, we move 1 shelf.
What does that mean? Because in order to get something out, with peak, you still have to specify the index.
Mm-hmm.
So what's seek actually doing?
So you're exactly correct. Peak ignores your current position, right?
Yeah.
So in that case, peak doesn't care where you currently are, right? You're right.
Yeah.
And peaks does care where you currently are, so that one makes sense.
Yeah.
Seek doesn't care where you are; it just moves to somewhere. But we haven't talked about extract yet, but I'll let you guess what that does. Great. So if we have a store, if we're talking about it in the same language of slots and views, we can kind of say, well, we've got a slot at every shelf, right? We've got a slot for every possible shelf number or every key. And we've got a view of the warehouse from every key, which is the idea of the forklift being positioned at each of these different slots, right? So I can imagine a warehouse where the forklift is at position 1 or at position 3. Those are different views of the same structure. It's a little bit more abstract. And of course, extract is the null query, the null operation. We don't move the forklift at all. We just say, get what you've got. Like, bring me what you're closest to. More abstractly, if we stop kind of thinking about the warehouse analogy, it's really just a getter and a key. So a function and an input to that function. So let's see some queries that we can actually run on this thing. So these are the types. We'll rip through this pretty quick. So get the position, get the shelf number from a store. Extract, get the value at the current shelf. And peek, I'll get the value at a different shelf. Okay, real examples now. We made it. Okay, so here we're going to define a different store. This one has nothing to do with a warehouse. The getter for our store is going to be this function, given an x, squared. Okay? And we have to always give it a starting point. It has to always know where to start. So we say start at 10, just because. Okay? So we've got that definition at the top. The position of this thing that we've created is 10. We started at 10. We said, hey, create the structure, position yourself with an input of 10. We can ask what that input is. We can also say, hey, what's at your current input? Notice we don't provide any input when we say extract. It already has it. It just runs the function. So it says, well, 10 squared is 100. And we can move to a different input and see what's there. So peek says, okay, well, I don't care where you are. Tell me what 2 squared is. And it'll do that. Just runs the function with the input you give it. Okay? And peeks, of course, can be relative. So if we already are at 10, we can say, well, move 2 up from your current position, which is 10, and square that. So 10 plus 2 squared, 144. Good. Yeah, so I've kind of talked about how there are these absolute and relative things. Some of them depend on your current position, some of them don't. Peak is absolute. Okay, so really this is all just the same stuff. We're going through here. I think we kind of get it. Good, making back some time. Okay, now we're going to look at some really cool stuff. Experiment is a combinator which we can use on the store comonad. So it's something specific to store which allows us to basically do some cool tricks with our queries. It's really annoying to peek at lots of nearby values. It just takes a lot of time. You have to pass the warehouse into the peek function. You have to do it again over here. You have to do it again over here. If you're taking an inventory of your warehouse, it's going to take forever. So what if we want to keep track of a bunch of results? Or maybe we want to fail based on certain criteria, like, you know, if you're in this part of the warehouse, I don't want you to bother going to get something. Or, whoops, sorry, there we go. So experiment gets a bunch of values relative to your current position, and does it with this weird signature. So it says, experiment, if you give me a function from some shelf number into some shelf numbers, maybe inside a context, this can be any functor. Then, if you give me the warehouse to look things up in, I will look up all of the things that are specified by all of the shelf numbers in your f. So, a little too abstract. Let's bring it down a layer. Let's say that our f is list. Okay? So, if you give me a function from a single shelf number into a list of shelf numbers, then I will look up that list of values that match the list of shelf numbers that you gave me. Okay? And we can also say, well, okay, if I give you a shelf number and you return a maybe of a shelf number, we can maybe even validate and say, well, if it's an even shelf number, I want you to get it, so I'll return a just of the same shelf number. And if it's an odd one, I don't want you to get it, so I'm going to return a nothing of that shelf number. And so, when we get the f out, well, if it was a nothing here, it'll be a nothing here.
Shouldn't f be traversal instead of functor?
No. Functor is great. It works. Yeah. So that might be some intuition that you might have, right? It kind of seems like we need to be able to build up the structure and then rearrange it. But actually, functor is enough. If you're really interested in that, you can look up the implementation of experiment. Okay, this is what it lets us do. We pass it this function, like I said. We're going to say, oh, given where we are, we're going to get the square of the number 10 less and the square of the number 10 more, and run it, and it'll get us both of those in the same spots that they ended up in the result of that function. Same thing here. Talked about, we can kind of do some validation if we want. So we can experiment to see if the number is above 0, and if it is, then we, then we'll return just that value, and if it doesn't match our predicate, then we won't. We're gonna, right, okay, so here's a kind of more interesting one. If you don't really get this one, that's fine, but we're gonna use the tuple functor, okay? So the tuple functor has the left element as context and the right element as the actual contents of the functor. So given a shelf number, we're gonna show that shelf number and keep the shelf number itself. When you run it through experiment, it's gonna replace this shelf number with the result, but leave the context the same. Which means, if we use this, we can say, okay, I'm just gonna extract. It will know what the input is, show it, but then also run the square function and give us the output. And we can do the same here. And we can move around and it still does the right thing. Okay. Cool, questions on all of the weird experiment stuff? It's a little abstract, hey? This one's a little tricky. Let's get to something a little bit more fun. Okay, so who here has seen Conway's Game of Life before? Yeah, good number? Okay, that's great. That's awesome. Oh, really? Sweet. So I barely even need to explain the rules. Okay. I can tell you Alexi's is probably going to be more efficient than ours, but that's okay. We're going to look at the rules here and say, I think most of you have probably seen this, but we have this grid and we have these cells, and if any cell has 2 or 3 living neighbors, that cell stays alive from iteration to iteration. We're kind of running a simulation. And if we have a dead cell that has 3 living neighbors, it will come to life, and in all other situations, the cell dies, unfortunately. Okay, and you can build cool stuff like this, right? Yeah. Awesome. So we want to build something that can compute these rules, right? So I have this helper in the library, and it just basically animates it and prints it out to screen. And we're going to build something that handles the rules engine behind whether cells are living or dying from step to step. All right. So let's figure out what we're going to do. We need to represent a 2-dimensional grid of cells, right? We're going to do it using this kind of warehousey feel. So we know we need some input, which is kind of analogous to our position, and we need some output. So we know that each cell is either alive or dead. That's what we need to store in our grid. So this is what I'm thinking. I'm thinking we can have a x-coordinate and a y-coordinate and a Boolean saying, true is alive and false is dead. Okay? I'm using the sum monoid here for reasons that will become clear. But you can treat them as just x and y integers for now. Okay, so this is basically what our function looks like. X, y, living or dead. Okay, I think we're all following? Cool. So we're gonna write this function. So we're gonna start off and we're gonna build a store monad given this getter function, which given a pair of coordinates tells us whether it's alive. And to start off our game, Conway's Game of Life, we're gonna seed some values which are alive or dead, just so that we can see how they progress over time. And we're just gonna do that using the setMember function on a pre-decided set of cells. Good luck visualizing that. But we'll see what it looks like. So, do we kind of understand? This is a function from xy coordinate, which will tell you whether that xy coordinate is in this list. in which case we say we're going to start as alive. Questions? Okay. So we can take a peek and say, well, 0, 0, okay, that's not in this list here. It doesn't appear. So it's going to be false, it's going to be dead. And 1, 0, well, that is in this list, first element there. And so that's going to be alive. And we're not going to get into this draw grid function, but it basically, I told it to just draw the first 3 by 3 elements of the grid, and we can see what that actually looks like. Okay? So we want a mutation, which goes from an entire grid of these alive or dead cells, and computes the next iteration, where we know whether each one is alive or dead. But that's complicated. We have to check each cell and look up its neighbors, figure out how many of them are alive or dead. We need to know whether that cell is alive or dead. Then we need to compute the next version without like mutating the grid, because then it's going to screw up all of the other ones. We have to do this everywhere at once. So let's break it down one layer into a query instead, because queries are just much easier to write. So we're going to write in this query form where we have this W of A into a B, which happens to be the same as the A. So this is a query which checks whether a given cell is alive. We're not telling it which cell to check. That's stored inside the store, right? It already knows where it is. So we can compute whether one cell is alive. We can extend this query over the entire grid without doing any extra work. Okay. So our recipe needs these ingredients. We need to know whether the current cell is alive or dead. Any ideas? Extract. Right on. Okay. We need to know the number of living neighbors. We'll come back to that. That's basically it, right? We just need to know whether we're alive and whether our neighbor, how many neighbors are alive. We don't even care which ones. So let's write a query to check the current cell. So you've got extract, and to get multiple neighbors, anybody have an idea? Experiment. Very good. Okay. So how do we write this? So this is, which one? Is this a mutation or a query? Query, right. Yeah, we have no structure in our output. So it must be a query. We're compressing it down. We're asking a question. We're saying, given a current position, how many neighbors are alive? So we need to check on the cells next door. So if we use this experiment, we can check all of our neighbors at once. How do we do that? Well, one way, we have auspiciously given a monoid instance for our xy coordinate. And it turns out that actually, if you have a tuple where each element is a monoid, you get a monoid for the whole thing, where it, appends the left elements and it appends the right elements, and does the right thing. So we can actually define our experimental function, which takes an index and returns some functor of indexes, where we take our current location and we offset it using just a append over all of these positions. So if we have, let's say we're at 0, 0. Actually, let's do something more interesting. Let's say we're at 10, 10. Well, if we append it here, we're going to get 9, 9. And we append it here, we're going to get 9, 10, and et cetera, et cetera. And you'll notice I've left out the cell itself, because we're not counting ourselves as part of our neighbors. So the index itself will not appear once we've done this fmap. Does this make sense? Okay. So we're computing a list wherein, given a coordinate, we have the coordinates in the list of all of the neighbors. Okay? Well, when we give this to experiment, it will take this function, pass it the coordinate, get the list of new coordinates, and then get the values at all of those spots, which is whether it's true, whether it's false, whether it's alive or dead. And we can say, well, if it's false, we're not going to count it as a living neighbor. If it's true, we are going to count it as a living neighbor. Maybe some of you haven't seen fold map before, but basically we're just folding over that list and counting up all of the ones that are true, or counting up all of the ones that are false. You can do this with filter. It's not important. We just get the count of the neighbors using this experiment. Questions about how we're using experiment here? Okay, so we are passing in this W, and then we're just running experiment on it, and then counting up all of the results in the list. Very cool. All set? That's all of the ingredients that we need. So now we can say, given a grid, we can get the current element, whether we're alive or dead, using extract. And we can find the number of our living neighbors using that function we just defined, calling that on the grid. And so our left element is whether we are alive or dead. The right one is how many neighbors are alive or dead. This is just a really concise definition of the Conway's game of life rules. So we determine whether we will live or die. Don't worry too much about the rules. They make sense. Okay, more questions? Okay. So we've written it once. Can we extend it? Yep. That's it. That's all we have to do. So now we've taken something that computes whether one cell is alive, and we run it everywhere. And we check whether all cells are alive. Now, question that I can see brewing in the back of your minds is how does it know which locations to run this on, right? Well, same as duplicate for a stream. When it duplicates, it fills every resulting position in the store with a copy of the store that's focused on its position, okay? So what that means is it's creating an infinite number of stores behind the function, so it's lazy, where each store is focused on every possible coordinate, okay? And then when we run this query over that duplicated part, it's going to query from each position and return the Boolean in the right slot. So quick note on performance. This will be good until you actually try to look inside. But one problem with this is because it's all based on functions, you can step once, that's fine, it'll be quick. But if you step twice, and then step 3 times, and then step 4 times, it'll really, really slow down because it doesn't do any caching. So to compute the 4th iteration, if you check cell 1, 1, it will actually recompute all previous 4 iterations for all of its neighbors manually from scratch. It's really bad. There is a way to fix this, but it involves representable functors, which I don't really have time to talk about right now. If you're super interested in it, come talk to me after. The basic idea is that you give it a way to represent this function as a data structure, and it will cache intermediate values. Then it gets quite fast. Okay. Questions on Conway's game of life?
The area, how far do you calculate when you represent the actual, when you print?
Right. So my print function, which is in the repo, you can check it out if you want. It's under comonads.store.conway, I think. I allow you to pass a range, like a square size, basically. So you can pass it 3, and it'll start at 0, 0, and calculate out. But technically, this is computing Conway's game of life over an infinite plane. Yeah. And you can peek at any given part of it, and it'll lazily figure out what should be there. Yeah.
Sorry, lazily meaning like if you look at a place where you've never seen before, it'll recalculate all the way from the beginning?
So it depends. If you've run iterations, you say, I want to look at this position on the 6th iteration, then yes, it'll calculate the previous iterations of all of its neighbors 6 times back. Yeah, that's right. And of course, you multiply 6 times back for 9 neighbors, and it gets pretty bad. Great. So, awesome. How much time do we have? Okay, we've got about 10 minutes left. So if there is anything in this set that you guys would like to go over, we can do that. Or we can try pulling out our laptops and see if we can actually implement this Comonad for store. And I can just kind of help you with that until we're done. Or we can add a new rule set, or we can move on to the next topic, but we only really have 10 minutes, so I'm not sure that's great. Does anyone have questions before we do anything else? Awesome. Okay. Let's see. Would anyone really like to try implementing some stuff on their laptop? Yeah, we got a couple. Okay. And who would like to Well, I mean, you guys can pick which one of these you want to do. So yeah, pull out your laptops. You can go in the repo. You can find Conway's Game of Life. And there's actually also an exercise version. So I think it's called Conway Exercise. And it's a shell version of Conway's Game of Life, which doesn't have anything implemented yet. So you can try implementing the thing that I've kind of gone through on screen yourself and see if you can figure it out. Or you can actually just try to implement the store Comonad all on your own. And if you have any questions, I'm totally free to help you, but also the answers are in the repo. Just, you can check them if you like. Cool. While people are doing that, is there anything you guys would like to fool around with? I can pull up a REPL. We can try some stuff out. I can show that draw grid function maybe.
I don't know.
And where is exercise for store again?
Oh, to implement the store Comonad for the store type. So
Where is it in repo? I mean,
Like the file path.
in the repo. So there's Comonads store.hs. There is a Comonad instance in there, so cover your eyes before you. But you can just delete that and try to re-implement it if you like. And you can actually see all of the implementation of the functions. If you like, you can actually delete the implementations of those as well and peek at the type signatures and see if you can work your way through it. Sorry, this isn't a little bit more organized. We actually ended up going faster than I expected. So I'll also point out tomorrow, I've got another 2 hours. So we've got 2 more Comonads to cover. We've got the env Comonad, which is co-reader. I guess I should have mentioned store is actually co-state. You can compare it to state by saying, well, okay, store has an S and a function to go from S to A. Well, state actually is a function which takes an S and returns an S and an A. So it kind of like flips the S from the inside of the tuple and the function outside. That's kind of how the co-analogy works. And tomorrow we're also going to go through the traced Comonad, which is co-writer. It's actually, in my opinion, a little bit more useful than writer is even. So that's going to be interesting. And if we go quick enough, we can hopefully get to some Comonad transformers and see what happens when you start stacking these on top of each other, which it's pretty wild what you can do. And if we have even more time, we can take a look at what it is if you start doing fixed points over Comonads. So we don't typically talk about that with monads, but basically what it can allow you to do is take one of these comonadic contextual operations and find out what happens if you follow every computation to its logical conclusion. So what does that mean? Well, for a spreadsheet Comonad, you can basically resolve computations which depend on multiple cells. And if those cells depend on other cells and those cells depend on other cells, you can write your code in such a way that it will resolve all computations for you automatically without doing anything extra. It's very cool. Another example of that is you can write Newton's method, where it will basically take a function as your comonad, compute the derivative, follow Newton's method until it gets close enough according to what you say, and it'll do that using fixed points. It's very cool. So you guys can think about which of those you'd be super interested in, and maybe we'll have some time to pick. If anyone has questions, just throw up your hand. I'll come on over. Yep. Yeah, the abstract ones get pretty tricky to implement.
I'm just trying to do stream.
Mhm.
And that's-
We got 5 minutes. I'll kind of live code a stream Comonad implementation. If anybody wants to follow along, you're welcome to. Awesome, thank you.
So, oh, I see.
Cool. So when I'm implementing Comonads, I usually do extract and duplicate because they're just kind of a little bit simpler. Extend usually just follows from duplicate anyway, so you can really manually write it out, and if you want, you can do a kind of fancy thing with it. But it's usually easiest to just allow it to be derived. But if you do want it, you can. Or if you want the duplicate version, you can. Let's do this. So here we can see two. Oops, there we go. Two possible implementations of extend. One in terms of duplicate and the other manually spelled out.
Cool. Yeah, mine's the same.
Awesome.
Just didn't use an infix notation for stream.
Fair enough. Yeah. Should be the same.
Yeah. And I used a let binding just to break up, for the extend just to work through it. But now I can just remove that now.
Sure.
So you can always define extend in terms of duplicate in that exact way?
Yes.
Okay, so is that part of the, is that baked into the class definition?
Yep. Okay. So we're all good here. You can feel free to keep working on this in your spare time. Hopefully see some of you tomorrow to keep on going. Hopefully you learned something. If you have any feedback for me, I appreciate it. You can come tag me after and say, well, I enjoyed it, but you could have done this to teach me better, or maybe you rushed this and I lost an intuition for this. That's super helpful to me. I'd appreciate it a lot. Otherwise, have a good rest of your monadic party.